All right, let me share my screen so we can see it in the recording. All right, for example, this problem. Get some stuff out of the way here a little bit. A particular fruit's weights are normally distributed with a mean of 326 grams and a standard deviation of 11 grams. The heaviest 11% of the fruits weigh more than how many grams? Now, I'm a big believer, and if you've watched the review, you know this to be the case. If I put this on the board, I don't know if you'll be able to see it in the recording. I'm a big believer in drawing a picture of that. So that's a normal curve. You got a value, whatever it is, X, and 11% of the weights are over to the right of that X. So what's to the left? 89%? That's all there is to it. Inverse normal, 0.89, mean standard deviation. That's it. That's all there is to it. Now, a lot of you have calculators that will do this. Now, I defaulted to showing it to the left because that's the default. But if you have a calculator that will do an inverse normal to the right, then do that. So what was it? 11%? And I don't remember what the mean was. What was the mean? 326 and 11. 326 and 11. And then we're going to go to the right because it's greater than. And actually, this is important that you know greater than is right to the right, because when we start doing hypothesis tests in the next chapter, it's important that you know that's an area to the right. Less than is an area to the left. So what do we get? 312. Okay, and so 11% of the fruit's weights are greater than 312. And I don't remember, what did they say to round that off to? Okay, so it's the nearest whole number, so that's 313, isn't it? To the nearest whole number. Now I could do it defaulting to the left. Would that be 0.89? Is that the only difference? What did I do wrong the first time? Oh, I used left. It's supposed to be right. You don't. I blame it on the cold. Oops. So 0.11. Right. And I got to hit enter. That's what I did not do, is hit enter to highlight the right. Now it should be the same answer, which it is. So 11% of the weights are above, and in this case, it's 339, correct, to the nearest whole number, because the number, the first decimal place is a 4. So you're just going to truncate, drop all those decimal places to round off to the nearest whole number. Okie dokie. So let's look at another one that's a 50%er. The 65% is a little problematic. If you do 70% or above, that's considered fairly normal. Outside the interval, and we talked about this one in class. We did this in class, and then I did it on the review. So twice you saw me demo this. If it's outside these two values, then what can you do? You can find the value in between and subtract it from 1, correct? The total area underneath the curve is 1. So if I know the area in between, if I know the area in between, I can find the area in the two tails. As a matter of fact, is that important in this next chapter? And the answer is yes. It's important that if I know that I'm trying to create a 95% confidence interval, that in the two tails is 5%, 2.5% over here and 2.5% over here. So it's important that I know that. So what are we doing here? I don't know, I can't read it. Area under the curve, standing on the outside the interval from negative 0.98 to 0.98. So can I find the area in between and subtract that from 1? Okie dokie. What was the next one? This very similar to the last problem. You're given the area under the curve and it's between two b's. A lot of you gave me a negative number and that's not what they're asking for. They're asking for b. B is positive. So they're asking for the positive number and you just found the negative. So what you did is you found the area to the left of negative b and put that in. That's not what they want. They want the area to the left of positive b. So they want b. That's what they want. So what is that going to be? I have no idea.
Confused me because on mine it said mine was negative, but I had put positive.
I'll look at it again. I don't know. Did I give you credit for it?
I think so.
Well,
I have no
I'll go look at it again.
Because I was looking at it and I was like, I'm pretty sure it's supposed to be.
I graded them twice, by the way. I graded every exam twice. I graded first problem by problem, then I graded your entire exam to make sure that everybody was getting. Yeah, I was doing the same thing for everybody. Okay, but this one, what's the area outside? So the area between is 0.4778. So 1 minus 0.4778 is the area in the two tails, correct? So half of that is in the left tail and half of it's in the right tail. So in the left tail is 0.4778 plus 1 minus 0.4778 divided by 2. So that's the area to the left, and that will give you B. So what you have to do, 0.4778. And is this important in the next chapter? Yes, it's important in the next chapter. So the total area under the curve is 1. So the area in the two tails is 1 minus 0.4778. I can type. So the area in the two tails is 0.522. Okay, so what's the area in each tail? Well, if I take that number and I divide it by 2, then the area to the left of negative b is 0.2611, and the area to the right of positive b is 0.2611. So that's the area in the two tails. So if I add that to 0.4778, then that's the area to the left of B. So do an inverse normal with that area, and that will give me positive B. Now, if you found negative B, I mean, you could find negative B by finding the area to the left of 0.2611, which is fine. That's negative B. You put the positive in the answer. If that's negative B, no positive B is just going to be positive. Does that make sense? I know, sort of. All right. What else do I want to rant and rave about? The 2 coin thing, we did that problem in class. I did it on the review. So I didn't have, I mean, we did it so many times. It was, and the probability is from previous chapters. It's simple probability. So it's something we've done several times. And I recommended in the review to create a table of all the probabilities and put those in your calculator. And I didn't see a lot of that written down on paper. I saw it more on the online class than I saw it in this class. But that's what I recommended. The values of 2 coins when you got dimes, nickels, and pennies is you can get what, 6 cents. What's the other one? What's the next one? 10,
2, 6, 10.
2, 6, 10, 11, 15, and 20. And then you just find the probabilities of each of those. And then to find the expected value, my recommendation was just put it in your calculator and find the one variable statistic. Because what you're doing when you're finding the probability is you're finding a relative frequency. So the relative frequency of you getting 2 cents is whatever that probability is. So you can put this in your calculator by putting the values, the 2, 6, 10, 11, 15, and 20 in one list, and then put the probabilities in the second list because it is a relative frequency. And so then you can just find the one variable statistics using that list and that frequency. And that was the easiest way to find the expected value, because the expected value is the mean of that distribution. All right, any questions on that? Some of these were really, really well. You got a couple, I got a couple that are 100%, so that's really good. The Alaska election thing, I was real happy about that. Although 20% of you left part of it unfinished. But those of you who did finish it, you got 100%. What's this one? I'm not sure. The only thing I can think of with this one, and I'd have to go back and look at the individual problems in your papers, is you didn't use the standard error of the mean. And why would I use the central limit theorem on this? Any clue? What's that? It's not, well, it's not only that. Do they tell me it's normally distributed? That's an assumption I made. But why do I use the central limit theorem? Because there is a sample. So they have a population from which they took a sample. And now we're looking at that they're mean weights. Mean weights. That means it's a central limit theorem. So the mean is the same as the population, but the standard deviation, you use the standard error of the mean. And in chapter 8, that is what we're going to do. When we use sigma, we don't use sigma. We use sigma over the square root of n. We use the standard error of the mean. All right? All right. Okay. So that leads me to this. And I've spent a little time Googling this morning, and I found a couple of polls, but I like this one the best, and it has nothing to do with it. It's on Fox News. The reason I like this poll the best is because they give me plus or minus. So this is a poll that was taken by the Wall Street Journal, and it was taken just a few days ago. 1,500 registered voters questioned October the 19th through the 22nd. And that's when this poll was taken. That's how many people that they polled. Now, you think that 1,500 is not a lot of people to poll in an election that's going to be, what, 100 million people voting in it? But we can look at that later if that's a sufficient sample size to get the information that we want. Of course, the sample has to be representative of all the people who plan to vote in the election, which can be kind of tricky to make sure your sample is representative, but that's probably a sufficient sample size to get this information. So they polled them and they asked them, who are you voting for? Okay, so according to this particular poll, 48% of the people who were polled said they're going to vote for Kamala Harris. 50% say they're going to vote for Donald Trump. But they give us down here a margin of error. So in the nationwide poll, it's plus or minus 3%. So what that means is she could actually be getting as low as 45% and as high as 53%. So somewhere in between the 45 and 53 lies the true population proportion of people who are going to vote for Kamala Harris. Now, Donald Trump is going to be what, 47 to 53. So somewhere in between 47 and 53% lies the true population proportion that's going to vote for Donald Trump. Now, both of these, with that margin of error, they're a statistical tie because of that margin of error. And that's true in every poll I've seen. They are statistically a tie right now. Now, in the battleground states, those are the states whose electoral votes will aid in the particular candidate winning the election. So in the United States of America, for the past 200 and something years, we have used the Electoral College to actually elect the president. Now, whether you agree with that or not, that's the way we do it. And the states have changed how they designate who the electoral votes go to. If you win the popular vote in some states, all the votes go to that candidate. Others, they divide. It's kind of weird. But anyway, in the battleground states, the ones that are going to win, the Electoral College, she's leading 52 to 46. And in that case, do you see what the margin of error is? 6.5%. So how do they figure this out? So my brother-in-law was asking me the other day when I was sitting in Colorado, I said, actually, it's statistically figured out. We figured it out using statistics. So what these are called confidence intervals. These are intervals from a lower limit to an upper limit that we are particularly confident that somewhere in between those two numbers lies the true population proportion that's going to vote for that particular candidate. And you can calculate this. It's very easy to calculate. Depending on how confident they want to be. So we've already done that in this class. We've already looked at finding Z values for a particular percentage under the curve. And that's what they're doing. They're saying, okay, I want to be 95% confident that the true population proportion is somewhere in between those two numbers. And that's how you calculate this. So do we see this right now, what you're about to do in chapter 8 right now in the real life? That's what we're going to do in chapter 8 is exactly how they did this. Okay. So chapter 8. We're going to be talking about confidence intervals. And we're going to calculate 3 types of confidence intervals. We're first going to be looking at confidence intervals for a population mean. Now, that's not what we just looked at in that data. That was a population proportion, which is also up there. And we're going to do that if we know the standard deviation of the population. So I have a population. I don't know its mean, whatever information I'm interested in for that population, but I know its standard deviation. I can figure a confidence interval. I can calculate a confidence interval if I know the population standard deviation. Now, typically, let's go back. I can do that using the normal distribution. Typically, if I don't know the population mean, I probably don't know the population standard deviation. And if I don't know the population standard deviation, I can use another distribution to calculate this confidence interval. That's called the t-distribution. And we used to call it the student's t. And we'll explain later why it's called the student's t. But we can use a distribution if I don't know the population standard deviation. And then I can calculate a confidence interval for a population proportion. And what's a proportion? A proportion is a percentage. So if you want to know, I can't think of anything right off the top of my head that's proportion except the example they get where they're talking. Anybody a baseball player in here? No baseball players? Okay, so if I wanted to know how many at-bats resulted in a base run, a base hit, I could calculate the number. I could take the number of bats I have, and I could divide into that the number of base hits. Well, base hits divided by the total, and I could get a proportion of base hits out of my total number of hits, at bats, excuse me, that I get. So I can calculate stuff like that. Okay, and then we're going to calculate the size. So we just talked about, is 1,500 sample size sufficient to calculate what we want to calculate? And you can calculate what sample size you need for a particular confidence level. Have you ever wondered the average number of M&Ms in a bag? You can calculate that. Okay, so the first thing we're going to look at is a single population mean using the normal distribution. And I'm debating whether to show this. I'm going to let you watch that. There is a video from Piper Parabol that you can watch on the confidence intervals. I don't know that it's particularly, I want to save time, so I'm going to skip it. Okay. We use sample data to make generalizations about an unknown population. The sample data help us to make an estimate of a population parameter. We realize that the point estimate is most likely not the exact value of the population parameter, but close to it. So we realize that taking a sample of 1,500 voters and getting that Kamala Harris has 48% of the vote and Donald Trump has 50% of the vote is probably close to the actual population proportion, but it's not exact. After calculating point estimates, we construct interval estimates, and that's that plus or minus 3%, called confidence intervals. This part of statistics is called inferential statistics because we're inferring something about the population from the sample. We are inferring that Donald Trump, whenever that poll was taken, has 50% of the vote compared to Kamala Harris, who has 48%. So if you're trying to determine the percentage of times you make a basket when shooting a basketball, you might count the number of shots you make and then divide that by the number of shots you attempted. In this case, you would have obtained a point estimate for the true proportion. And we use P with a little hat over the top of it to represent the sample proportion. And it is a point estimate of the true population proportion. So P hat means the proportion, the percentage you get from a sample. Suppose you were trying to determine the mean rent of 2-bedroom apartments in your town. You might look in the classified section of the newspaper, probably not anymore, write down several rents listed and average them together. You might go to apartments.com these days. You would have obtained a point estimate of the true mean. So the sample, when you calculate the average of the sample, you calculated X bar. And X bar is a point estimate of the true population mean of 2-bedroom apartment prices, rent. So P hat is the proportion of a sample. X bar is a mean of a sample. A confidence interval is another type of estimate, but instead of being just one number, like a proportion or a mean, it's an interval of numbers. It provides a range of reasonable values in which we expect the population parameter to fall. There's no guarantee that the given confidence interval does capture the parameter, but there's a predictable probability of success. And for those of you who's been a while since you had algebra, the way that we write an interval is we use parentheses with a comma, and we put the lower limit in the first spot and the upper limit in the second spot. And intervals always go from the smaller number to the larger. Always. It always goes from left to right. Always. So this number is always smaller than that number. Always. Okay? So if you see this notation, parentheses with a comma separating two numbers, that means that on the number line, we have a lower and we have an upper. And somewhere in between lies our true population parameter. Somewhere in between those two numbers is where that lies. Suppose we do not know the population mean mu, the mean number of songs a consumer downloads a month from iTunes. Maybe it's Spotify these days. But we do know that the population standard deviation is sigma equals 1. So if I know the population standard deviation, I can just use the normal distribution for this. We take a sample size of 100 and calculate the sample mean of 2. So the sample mean, X bar, is 2, and sigma, the population standard deviation, is 1. Then, by the central limit theorem, because we are looking at sample averages, so we're going to use the central limit theorem, the standard deviation for the sample means is sigma over the square root of n. So we use this because we are looking at samples. And when we're looking at samples, we're going to use that standard error of the mean. That's what this is called. The standard error of the mean. You can just call it the standard error. Okay, so we take the population standard deviation, we divide that by the square root of our sample size, and we get 0.1. 1 divided by the square root of 100 is 0.1, because that is 1 over 10, which is 0.1. Okay, so now we can find this interval that we are confident that the true population mean number of songs downloaded from iTunes in a month is somewhere in between these two numbers. So from the empirical rule, I know that approximately 95% of all my sample averages is going to be somewhere in between plus or minus 2 standard deviations from the mean. That's the empirical rule. So I know that plus or minus 2 standard deviations from the mean is going to somewhere, it's going to contain the true population mean 95% of the time. I think I said it all messed up. Okay, so let's just take the mean, which is 2, and let's multiply that by the standard error of the mean, which is 0.2. So X bar is within 0.2 units of sigma, 2 standard deviations, and this is standard error. So we take the 2 standard deviations, we multiply that by the standard error, and we get 0.2. Because X bar is within 0.2 units of mu, which is unknown, then mu is likely to be within 2.2 units of X bar in 95% of the samples. So 95% of the samples that I take, mu is going to be somewhere in between X bar plus or minus 0.2 standard deviations, or 0.2. I said 2 standard deviations. That is not correct. That is just a number. That is called the margin of error. The population mean mu is contained in an interval whose lower number is calculated by taking the sample mean and subtracting 2 standard deviations, and whose upper number is calculated by taking the sample mean and adding 2 standard deviations. In other words, mu is between X bar minus the margin of error 0.2 and X bar plus the margin of error 0.2. And the margin of error in this case is calculated by, if I'm not want to be 95% confident then I know 95% is 2 standard deviations. So I take 2 standard deviations and multiply it by the standard error. Okay, did I mess that up sufficiently? Okay, so if we take X bar, which was 2, and we subtract 0.2, we get 1.8. If we take X bar and we add 0.2, we get 2 plus 0.2 is 2.2. So we say that we are 95% confident that the unknown population mean number of songs downloaded from iTunes per month is somewhere between 1.8 and 2.2. So the 95% confidence interval is, you see those parentheses? Parenthesis 1.8 comma 2.2, somewhere between 1.8 and 2.2. So we are 95% confident, or in 95% of the samples that we take, we will see that the true population mean is between 1.8 and 2.2. The 95% confidence interval implies 2 possibilities. The first, which we just said, either the interval 1.8 to 2.2 contains the true mean mu, or our sample produced an X bar that's not within 0.2 units of the true mean. And the second possibility only happens 5% of the time. If we're 95% confident that the true population means somewhere between 1.8 and 2.2, then 5% of the time it isn't. Remember that a confidence interval is created for an unknown population parameter like the population mean mu. Confidence intervals for some parameters have the form the point estimate, which is either the mean or the proportion of the sample. Point estimates are calculated from a sample. We do not look at confidence intervals for standard deviations, by the way. The point estimate minus the margin of error, the point estimate plus the margin of error. The margin of error depends on 3 things. It depends on what confidence level you are stating. It depends on your standard deviation, and it depends on your sample size. So the margin of error is calculated using how confident you want to be, what is your population standard deviation, and what's the size of your sample. And we talked about this, all right. Construct a confidence interval for a single unknown population mean mu, where the population standard deviation is known. So somewhere in the problem, they tell you sigma equals, or the population standard deviation is. We need X bar as an estimate for mu, and we need the margin of error. The margin of error is called the error bound for a population mean, or EBM. So EBM is the margin of error. The confidence interval estimate will have the form, the point estimate, which is the sample mean, minus this error bound of the mean, to the sample mean plus the error bound of the mean. So it's going to be an interval from X bar minus the EBM to X bar plus the EBM. How do I calculate it? I guess it should be looking at my notes somewhere along here. Okay. The calculation of the error bound of the mean depends on the confidence level, which we abbreviate CL. The confidence level is often considered the probability that the calculated confidence interval estimate will contain the true population parameter. However, it's more accurate to state that the confidence level is the percent of confidence intervals that contain the true population parameter when repeated samples are taken. So if we repeatedly take samples of a population, then we are so confident that this interval contains the true population mean. There's another probability called alpha, and that is that Greek letter right there, alpha. It's related to the confidence level. Alpha is the probability that the interval does not contain the unknown population parameter. Mathematically, alpha plus the confidence level is 1, or alpha is 1 minus the confidence level, or the confidence level is 1 minus alpha, however you want to look at it. All right, let's do one. Suppose we've collected data from a sample. We know the sample mean, but we do not know the mean for the entire population. The sample mean is 7, and the error bound for the mean is 2.5. So if X bar is 7, and the error bound of the mean is 2.5, then what's the confidence interval? So the confidence interval the lower bound, lower limit, whatever you want to call it, is equal to the mean. Actually, let's write that formula down. The mean minus the error bound of the mean. So it's going to be what? 7 minus 2.5? So what's the lower limit of our confidence interval? Is that 4.5? Okay, what's the upper bound? Upper limit. It is X bar plus the error bound of the mean, which is what? 7 plus 2.5? Is that 9.5? So what's the confidence interval? The confidence interval is 4.5 to what? 9.5? Now, depending on whatever my confidence level is, which is not given in this problem, there is no confidence level given. For example, if the confidence level is 95%, then we're 95% confident that the true population mean is somewhere between 4.5 and 9.5. Or in 95% of the samples that we take from the population, the true population mean will be between 4.5 and 9.5, 4.5 and 9.5. Okay, so we need a formula for the error bound of the mean, and the error bound of the mean depends on 3 things: the confidence level you're using, the standard deviation of the population, and your sample size. So if it depends on the confidence level, it depends on the Z value that corresponds to that confidence level. That's why we made you do all that stuff in the last chapter. A confidence interval for a population mean with a known standard deviation. Again, if you know the standard deviation of the population, you may use the normal distribution. If the problem doesn't tell you what the population standard deviation is, you're going to have to use another method. Can't use the normal distribution. The confidence interval for a population mean with a known standard deviation is based on the fact that the sample mean follows an approximately normal distribution. That's the central limit theorem. The distribution of sample averages will be normally distributed no matter what the underlying distribution looks like, as long as we take a sample of sufficient size. Now, if the underlying distribution is normal, we can use the central limit theorem no matter what size sample we take. When we know the population standard deviation sigma, we use a standard normal distribution to calculate the error bound of the mean and construct the confidence interval. We need to find the value of z that puts an area equal to the confidence level in decimal 4 in the middle of the standard normal distribution. That's why we made you do this over and over and over again. So the z-score that has an area to the right of alpha over 2 is denoted by z sub alpha over 2. What's that mean? You have a confidence level of 95%, 0.95. Then alpha is 1 minus 0.95. So alpha is 0.05, correct? If I divide that by 2, that gives me alpha over 2, which is what, 0.025? That is the area to the left and to the right. So if I draw a picture, my confidence level is 0.95, 95%. Then that means that 95% of the area is between these two z's, and that's negative, and this is positive. Okay, so if that's 0.95, then in each tail, one minus 0.95 divided by 2 is in each tail. So is that 0.025 and 0.025? So z sub alpha over 2 then can be found. Then the area to the left of z sub alpha over 2 is what? 0.95 plus 0.025? Is that 0.975? So z sub alpha over 2 is inverse normal. 0.975, 0.1. Now, if you have a calculator that supports center, you can just use center. Okay, so let's go see if it is 1.96. Let's go find out. Okay, so let me clear out all this stuff. So we're going to go inverse normal, second distribution, number 3. 0.975 is to the left of z sub alpha over 2, or z sub 0.975. 0.975. Area mean is 0, standard deviation of 1, because it's a standard normal distribution. And most calculators default to left. So go ahead and paste that back into the home screen. And we get 1.96. And that's something, maybe I should put that on the formula sheet. For a confidence level of point, you don't really need this because you're going to let your calculator calculate the confidence intervals in just a minute. But the z value for a confidence level of 0.95 is always 1.96. Now, if you have a calculator that supports if you have a calculator that supports center, you put the area in there, 0.95, and then just go down there and highlight center. Had it better be the same answer? And you'll notice that when you say center, it gives you the negative. So it gives you the z sub alpha over 2 over here, and it gives you the positive. So in between negative 1.96 and 1.96 is 95% of all the data. Okay? So that's how I calculate a Z for a particular confidence level. All right. So the error bound of the mean is calculated as follows. You take Z sub alpha over 2, the positive Z, you multiply it by sigma and divide it by the square root of n. So you take the Z value and you multiply it by the standard error. Okay? And Z sub alpha over 2 depends on whatever confidence level you've chosen. So that is the formula for the error bound of the mean. Okay, so let's do an example of finding the error bound of the mean. Suppose scores on exams are in statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. So I know I'm going to use the normal distribution for this because they tell me the population standard deviation. Bless you. A random sample of 36 scores is taken and gives a sample mean of 68. Find a confidence interval estimate for the population mean exam score, the mean score on all exams. Use a 90% confidence interval for the true population mean of the statistics exam scores. So I need to find Z sub alpha over 2. Okay, so I have a 95% confidence level. So if I draw myself a picture, that was the other thing. There weren't a lot of pictures on this exam. I'm all about drawing pictures. So the area in between these Z sub alpha over 2's is what? 90%? So what's in each tail? 1 minus 0.9 divided by 2. So take the total area of the curve, which is 1, subtract the confidence level. Actually, we could write that down. So it is 1 minus the confidence level divided by 2. That is alpha over 2. Okay, so what is that? 0.1 divided by 2, is that 0.05? So we have 0.05 over here. We have 0.05 over here. So what's Z sub alpha over 2? Z sub alpha over 2 is what? An inverse normal? Area to the left is what? 0.95? Right? Got 90% in between. We got 5% over here in the tail. So is it 0.95? 0, 1? What do you get? You get 1.645. Now, being old school, been around forever, this is the other Z sub alpha over 2 we always memorized. So we always memorized for 95%, which is what, 1.96? And we always memorized for 90%, which is 1.645. Okay, so now that I know the Z sub alpha over 2, how do I find the error bound of the mean? The error bound of the mean is Z sub alpha over 2 times sigma divided by the square root of n. So we have what? 1.645 times, what was my standard deviation? 3 points, right there. Divided by, my sample was what, 36? So once you calculate the Z value using the normal distribution, you can just multiply that by 3, the standard deviation, and divide that by the square root of 36. I happen to know the square root of 36 is 6, but if you don't know that, that's fine. And let me go over there and do this real quick. So we have an inverse normal. 0.95, correct? 0, 1, and we did left. Again, if your calculator supports center, just put 0.9 in there and highlight center. 1.64485, I'm going to multiply that by the standard deviation, which was 3, correct? And divide that by the square root of 36. So what's the error bound of the mean? The error bound of the mean is 0.8224. Okay, so let's write that over here. Now, if you had used the rounded off value for z sub alpha over 2, you would have gotten 0.8225. This is 8225. Man, there's not even close to 8225. By the way, that was the other one. Your answer on your paper was 0.4, and then you put in your in the field 0.04. That's one of those, like I just wrote down 0.885, and it wasn't even close to 0.8225. And I gave you credit for that. I tried to. If it's correct on your paper, I try to give you credit. Okay, so that's calculated using z sub alpha over 2 is 1.645. So you do get a little round off error if you do that. Okay, so now how do we calculate the confidence interval? So the confidence interval is found by taking the mean and subtracting the error bound of the mean, and taking the mean and adding the error bound of the mean. Okay, so what did we have for the mean? The mean was 68, is that correct? 68 minus 0.8224, 68 plus 0.8224. So what's the confidence interval? 67.1775 to 68.822. So in 90% of the samples, we had a confidence level of 90%. In 90% of the samples, we would expect the true population mean to be somewhere between 67.18 and 68.82. And we probably shouldn't carry it out to more than a couple of decimal places, to be truthful, because our mean was what? A whole number. So we probably shouldn't carry it out to more than one decimal place. Would you like to know the easy way to do this? You know, someone, I'm not going to say who came in my office, but I've had the online class say this to me too. So a lot of this class is just figuring out how to get it in your calculator. And I say, unfortunately, that is true. And why do I say unfortunately that's true? Because if you just do a rote, let's put the numbers in, you kind of lose the meaning of why you're putting those numbers in. So I try to reiterate every time we do this, this is why you're getting this interval. And is it important? And if you look at the polling, is that important? I don't know how important polls are, you know. I don't know. I mean, it's going to turn out the way it's going to turn out, whatever the polls say, but. All right, so let's go over to our calculators. And I am going to go to a different place than I've been so far this semester. I'm going to go to my stat menu. And we have already been in the stat menu quite a bit in the edit and the calculate, because we have put data in lists and then we've calculated one variable statistics. Okay, we're going to go to the tests menu. which we're going to spend a lot of time for the rest of the semester in the test menu. And look at number 7 and number 8. Number 7 is a Z interval. That is using the normal distribution to find a confidence interval. Number 8 is a T interval, which we will talk about next Tuesday. A Z interval is what you use when you know the population standard deviation. It is known to you. So we're going to go down and highlight number 7 or hit 7 on our keyboard. And then we have all sorts of stuff that we get to put in. The first line says input. Are you inputting the actual data? So you have the raw data and you're going to put that in, or are you going to put in the statistics? So I know the mean, I know the standard deviation, I know the confidence level, so I'm going to use that. So in this particular example, I know the mean, right? It's 68. So I'm going to go over and I'm going to highlight stats. So if I know the mean and I know the standard deviation, that is what I use. Okay, what was the standard deviation? Was it 3? Yes. And I don't have to put 3 divided by the square root of n. I just put in 3. And what was my X bar? Was it 68? What was my sample size? Was it 36? Am I using a 90% confidence level, 0.9? Is that what we got before? So what's the lower limit of my confidence interval? 67.178. What's my upper limit? 68.822. So your calculator calculates the error bound of the mean for you, and then subtracts that from your mean, and then adds it to the mean to get you the confidence interval. Well, that's kind of sweet. Why didn't she show you that? Because it's important you know where the error bound of the mean comes from. Where does it come from? It comes from the confidence level that you're interested in. It comes from your standard deviation, and it comes from your sample size. Okay? Well, that was easy. All right, I think we have time for this. Let's give it a try. The specific absorption rate, SAR, for a cell phone measures the amount of radio frequency energy absorbed by the user's body when using the handset. Every cell phone emits RF energy. Different phone models have different SAR measures. To receive certification from the Federal Communications Commission for sale in the United States, the SAR level for cell phones must be no more than 1.6 watts per kilogram. The table on the next slide shows the highest SAR levels for random selection of cell phones. Now, this data is pretty old, by the way. Find a 98% confidence interval for the true population mean of the specific absorption rates, SARs, for cell phones. Assume the population standard deviation is sigma equals 0.337. So I know I'm going to use a Z interval because they give me the population standard deviation. They tell me what sigma is. Now, what you have to do, because they're giving us raw data, you have to put this in your calculator in a list. So there's a couple of different ways you can handle this. You can certainly do a Z interval from data, put the data in and tell your calculator where the data is. Or you can run the one variable statistics, find the mean, use that in the confidence interval to find the confidence interval. I mean, it's just probably as easy to let your calculator do all this for you. I could give you 5 minutes to put this in your calculator. Do you want to try to put it in your calculator? Or you just want me to demo it? What's that? Demo. You're nodding. Okay, so I put these 30 data points in my calculator. I did that this morning. I go, oh man, I gotta put all that data in. So I'm gonna go stat, edit, and you can see in my L1 list is all that SAR data, okay? So I want to calculate the confidence interval for this data. And what's my confidence interval? 98%. I'm going to calculate a 98% confidence interval for this data. So I'm going to get out of here. I'm going to go stat, tests, and I'm going to use a Z interval. And I'm going to use a Z interval because they give me the standard deviation of the population. They told me sigma is equal to whatever it's equal to, which I'm going to have to know what it's equal to be able to do this. Okay. But now, instead of putting the stats in, I'm going to use the data that I put in. So I'm just going to arrow to the left and highlight data. And then it just asks me, okay, what's the standard deviation? What was the standard deviation? 0.337. So we put that in. I put my data in L1. So I go second, 1. Frequency is 1. I don't have any frequencies. But if you had data that had frequencies, you know, you had 12.1s and I have 5.2s, I'd put the frequency. I'd put the data in one list and the frequency in another list. Okay, what was my confidence level? 0.98. So what's my confidence interval from 0.8806 to 1.1669? The mean of that data is 1.0237. And then it tells you the standard deviation of the sample data and the size of the sample. So what do I know here? 98% of all the samples I take of cell phones, the SAR, the average SAR is going to be between 0.8806 and 1.1669. So the sample mean is 1.0237, but the true population mean is somewhere in between 0.8806 and 1.669. And in the slides, we calculated old school by finding the error bound of the mean. A Z value for 98% is a Z value for 0.01 or 0.99 to the left of Z sub alpha over 2, which is 2.326 times the standard deviation of the population divided by the square root of the sample size. So the error bound of the mean is 0.1431. So our sample average is 1.024, and the confidence interval is 1.024 plus or minus 0.1431. Okay, I got 5 minutes. All right, what is the effect of changing your sample size? If I increase the sample size, the error bound of the mean gets smaller. If you increase the denominator of a fraction, the fraction gets smaller. So as the sample size goes up, the error bound of the mean gets smaller. So your confidence interval gets narrower. So as n goes up, the error bound of the mean goes down, and the confidence interval gets smaller, narrower. What happens if I decrease the sample size? Well, exactly the opposite. If I decrease the sample size, the error bound of the mean gets bigger, the confidence interval gets wider. Now, if I increase the confidence level, that changes Z. If I increase the confidence level, then Z gets bigger, the error bound of the mean gets bigger. So if I increase the confidence level, the confidence interval gets wider. If I decrease the confidence level, the confidence interval gets narrower because Z gets smaller. Okay, last but not least. Suppose you want to calculate a sample size given a margin of error in the sample. You use this formula right here. And this formula is only found in the slide, so you might write it down. So N, it's the sample size you need for a particular confidence interval, is z squared, which you find, that's the z sub alpha over 2. So that is based on the confidence level you're using, times the standard deviation of the population squared, divided by whatever error you want. So if I'm interested in predicting plus or minus 5 points, that's the error bound of the mean. So a population standard deviation for the age of Foothill College students is 15 years. The confidence level is 0.95. And the error bound, the margin of error, is 2. I want to be 95% confident that the sample mean age is within 2 years of the true population mean of the Foothill College students. Okay, so how do I calculate this? Well, I need to know Z. So Z for a 0.95% confidence level, what was that? Did you write that down? 1.96. So that was something we calculated earlier. So we take sigma over times Z over N, and we square it. No, Lisa. Margin of error. And you can square each one and do this division. I just do the division and then I square it. So what was my standard deviation? 15. The Z is 1.96 divided by the error bound. I want it to be within 2. I square that. And I get 216.09. Okay, everybody awake momentarily? Always round up. Doesn't matter if you've got decimal places to the right, you round it up to the next whole number. So 216.09, we round up to 217. So your sample size should be 217 students if you want to be within 2 for your margin of error. All right, none. Are there any questions? All right, we'll see you next Tuesday.